Today I need probably 10 minutes to finish up on intermolecular forces. We want to tell the story of cell membranes. We want to tell the story of why you use eggs when cooking. And we want to tell the story of the hydrophobic effect. Then we're going to move on to shapes and structures of organic molecules as we talk about something called conformations, which is going to involve rotation around carbon-carbon bonds. So first, you saw last time that if a molecule has one polar head group and then a nonpolar tail, and we can mix and match what the polar head group is, and we could change what the nonpolar tail is. In fact, your problem set gives you this kind of question directly, showing you several structures that have a polar head group and one nonpolar tail. Those tend to form micelles and are detergents, in other words, soaps. Those tend to solubilize greasy stuff and allow you to wash them away. And the reason for that is their conical shape, as we talked about last time. They sort of, when they assemble to protect their nonpolar tails from water, and we will talk about why that is, but when they assemble side to side, you get some curvature, you get a spherical assembly. Now, one thing we could imagine is, what if instead of one nonpolar tail, we had two? So we're going to go back to the structure of a triglyceride, only we're going to only put two fatty acid tails on the glycerol backbone. And then on the other group, we're going to put something else. So this is called a diacyl glycerol. It's not a triglyceride because instead of having three fatty acids, we only have two. And on the other oxygen of the glycerol chain of a triglyceride, there's going to be a polar head group. And this almost always, in biology, this almost always involves a phosphate group. And then usually something is attached to that phosphate group. In this case, it's a two-carbon chain with a nitrogen on the end of it. You don't need to memorize this, but you may hear about this later in biochemistry. This molecule is called phosphatidylcholine, and it is an example of a lipid. And lipids are, in general, biological molecules that are nonpolar. But if you relax your eyes just a little bit, you can see the polar head group. And then you can see the two nonpolar tails. And the change from one tail to two seems subtle, right? It should have the same overall properties. But the change from one tail to two makes it so the diacyl glycerol with the polar head group has a more cylindrical type shape. I don't like that cylinder. Let me try again. Okay, so if you put this in water, it's going to want to assemble side to side to limit its exposure to water, and we'll talk about why that is in a little bit. So it's going to do the same kind of self-assembly that the detergents do. But instead, because it's cylindrical and not conical, you don't get as much curvature. So you can see that side-to-side assembly of these phosphatidic acid molecules, these diacyl glycerols, side-to-side assembly gives you mostly what we might call a monolayer. And if you think about putting this in water, that doesn't help you very much if your goal is to keep the nonpolar stuff from water, because water would be over here and over here. And so there's still some nonpolar surface area exposed. Does that Makes sense. So because there's not a lot of curvature, the thing's not curving back on itself to make a sphere. So what happens instead is one of these monolayers will associate with the other, and they'll put their nonpolar interior, they'll put their nonpolar edges together. And what you have here is then what you may have learned about in a biology class that's called the lipid bilayer. Except we can't spell bilayer apparently. And this is what cell membranes are made of. So cell membranes have an outside and an inside, and that lipid bilayer extends forwards and backwards, front and back in 2 dimensions, but then it eventually curves back on itself, and then you have an inside and an outside. That's really important in biology. Membranes are what makes you different from everything else that's not you. It's a boundary, right? And biology uses membranes to put things into compartments. The mitochondria has a membrane around it. Vesicles inside the cell have membranes around them. Some viruses have membranes. So this is an important part of biology, and it all works for this same basic effect. Polar head group, nonpolar tail. Only 2 nonpolar tails allow it to make a membrane. 1 nonpolar tail, and it would be micelles and detergent. Is that questions about that? Yeah.
So when there's only 1 polar tail or nonpolar tail,
yeah,
it will form a bubble. But when there's 2, it will form this bilayer.
Right. When there's 1 nonpolar tail, it can form bubbles, or it can form a micelle, which has, the polar head group and the nonpolar interior. But when it's got 2 nonpolar tails, it'll form a bilayer. Yep. And you can, as I said, you can change up the structure of the nonpolar tail, and you can change up the structure of the polar head group. There are many diacylglycerols in biology. There's some variation in what these polar head groups are. And we'll talk maybe more about that in 352, and you'll definitely get that more in biochemistry. Okay, so we've done membranes. We need to talk briefly about, that was supposed to be faster than it was. We need to talk briefly about emulsifiers. So if you're ever cooking, baking in particular, actually let's just leave that and then copy. This molecule phosphatidylcholine I told you about, which is a lipid, is also a major component of egg. And so when you crack an egg, in addition to the proteins that are present in the egg, the albumin and the other proteins in the yolk, there's also a fair number of diacylglycerols or phosphatidylcholine that's present in the membranes in the egg. When you bake, you use egg usually when you need to mix together water and some kind of fat or oil. So if you're making cookies, probably the source of fat is butter. Then you have a little bit of water, maybe some milk. You've got some carbohydrates in there. But as you know, oil and water don't like to mix. You could shake up a bottle of oil and water. In fact, I should have done this. I've done this before where I brought in an egg and we cracked it and I shook up the bottle and you could see that it would help mix the oil together. In any case, because of this molecule, which is what we might call amphipathic or amphiphilic, it has 2 different characters in it. It has a nonpolar side and then it has a polar side. Molecules like this are good emulsifiers, meaning they help oil and water mix. They have a portion that can interact with the oil, portion that's comfortable in oil, nonpolar, and then they have a portion that's comfortable in water. And so, of course, you could also do this with soap. As you know, detergents help soap and water mix, but we don't use soap in baking mostly because, I don't know, it might taste bad. So in egg, you have a molecule that's kind of like a soap or a detergent. It's got 2 nonpolar tails instead of 1, but it's good at helping oil and water mix. And you can try this at home if you want. Put some vegetable oil and water in a jar and crack an egg into a separate container and beat it. like you're making scrambled eggs, but then instead of cooking the scrambled eggs, you just pour the egg in the water and the oil, shake it up, and do a control experiment without the egg, and you'll see that without the egg, the oil and the water separate out very quickly. With the egg, they separate out much more slowly. And in fact, mayo is just water and oil and egg shook up to make an emulsion, and then maybe some spices in there too. So homemade mayo, I don't know that I'd recommend actually trying that, but if you want to, knock yourself out. Okay, that's emulsifiers. Questions about that? You just need a non-polar tail and a polar head group, and then you can cause water and oil to mix. So that's why you use egg while baking. Okay, finally, the hydrophobic effect. To understand this, we got to go back to what we said, I think last time, about the difference between water and ice. This you must understand, or else what I'm going to try to tell you about why oil and water don't mix will not make sense. So, remember, in ice, the hydrogen bonds between water molecules are rigid, they're less transient, there's much less entropy. In water, liquid water, the hydrogen bonds are exchanging quite rapidly, molecules are moving fast relative to each other, and there's high entropy or disorder. Okay, so you already know that oil and water don't mix, but let's imagine what happens if they did. One way to understand why something doesn't happen is to imagine it happening and then to see that doing so is unfavorable, okay? So just imagine in a liquid of any kind, the molecules are moving pretty rapidly relative to each other. So pure liquid water, as I said, a lot of entropy. Pure liquid oil, a lot of entropy. The oil molecules are moving rapidly relative to each other. Now let's just zoom in on the non-polar portion, on one of those fatty acid tails of vegetable oil, and look at what happens when you put that molecule in the presence of water, if you were to dissolve it in water. All right, so we'll just put a squiggly line, meaning there's other stuff over here on the left, but on the right we'll put a non-polar tail of some kind. And let's just suppose that we're zooming in on a triglyceride that is, for our purposes here, dissolved in water. It may be useful to put in hydrogens that are implied but not shown. I'll do that at least in a couple of cases, and then you can imagine the rest of them because we don't have huge amounts of time. Let's just, and then I'll try to shade in, whoops, well, that's that then. Try to shade in sort of all the space that's taken up by non-polar bonds, and we'll just imagine those other hydrogens there. Okay. Now, of course, if this oil molecule were dissolved in water, there has to be a place where there are water molecules nearby the non-polar stuff. But those water molecules can't hydrogen bond with the non-polar stuff. Why? Well, because the non-polar stuff's non-polar. There's not a lot of electronegativity difference between a carbon and a hydrogen. So that means the water molecules in the immediate vicinity of the non-polar stuff are going to have less than the ideal number of hydrogen bonds. Do you remember how I told you in liquid water and even in ice at any given point, each oxygen is hydrogen bound to two other hydrogens? Because the oil is taking up space that the water molecules would normally take up, the water molecules in the immediate vicinity of the oil, they don't have as many hydrogen bonds. So what that does is it makes their remaining hydrogen bonds even stronger. And so I'm going to draw a network of hydrogen bonds between the water molecules that are immediately surrounding the oil, or the nonpolar part of our molecule. Now, because we're a little short on time, what I'm going to do, instead of drawing this network of hydrogen bonds around the whole molecule, is I'm going to highlight it in blue, and then I'm just going to continue it like this. But you have to imagine that you've got a tight network of hydrogen bonds around the oil molecule, okay? So because the oil molecule can't hydrogen bond with water, the water molecules nearest the oil have fewer but stronger hydrogen bonds. This causes the water molecules near the nonpolar surface area of the oil to slow down. And they become almost an ice-like cage of water that surrounds the oil. They're slowing down, they're moving more slowly, they have lower entropy. In other words, putting the nonpolar thing in water causes some water molecules to freeze out in an ice-like coating around the nonpolar stuff. That's a loss of entropy, and it's unfavorable. And in fact, if this oil molecule were to back out of the water and go back with its fellow oil molecules, all of these slowed down water molecules would be released back to the liquid phase, and their entropy would increase, okay? So the hydrophobic effect, the reason oil and water don't mix, this thing we call the hydrophobic effect, is because exposure of nonpolar surface area in a molecule to water causes water entropy to decrease. And that's unfavorable, as you know from that equation about delta G equals delta H minus T delta S. And the reason water's entropy decreases is because of this ice-like coating that water forms around the nonpolar surface area. And the reason that forms is because water can't hydrogen bond with the nonpolar stuff. Okay, that's the hydrophobic effect. Questions about that? Your problem set will ask you to explain it. I sometimes write multiple choice questions on an exam about it where you have to explain it. Some people get it wrong. Some people say, well, the hydrophobic effect comes from the fact that van der Waals interactions between, or dispersion interactions between the nonpolar groups are just so strong that water can't break them apart. That's wrong for many reasons, one of which is hydrogen bonding interactions are stronger than van der Waals interactions. But the big reason is, as I said, it's not that the van der Waals interactions between the oils is strong, they're not, but it's that water can't replace those interactions with anything favorable. And in fact, water forms this low entropy ice-like coating around the nonpolar stuff, and that's unfavorable. Okay, so it's better for the two never to mix in the first place. Questions about that? You're like, duh, we already knew that. Go ahead.
Maybe you explain this, but why would the water not be able to have, I forget the term for it, but have the oxygen have interactions with hydrogens on the nonpolar?
Right, why can't the oxygen on water interact with the hydrogens on the nonpolar stuff? It can do dispersion interactions, van der Waals interactions, or induced dipole interactions, but it can't do dipole-dipole interactions because the hydrogens on the nonpolar stuff are about the same electronegativity as the carbon. So there's not a big delta plus on those hydrogens. Yeah. Okay, what else? All right, well, that's it on the non-covalent interactions. So now we want to talk about shapes of organic molecules. And I'll teach you how to draw this, but it's best to see it in animation first. So we'll go to, where is it? Molecules, the Molecules app. And we'll look at our gallery of molecules, and we're just going to look at the molecule ethane, which is our simplest one of our simplest two carbon molecules. Now this is an actual what's called molecular dynamics simulation. There's actual physics going on in the background that are predicting how this molecule is going to move. we can make the simulation faster and see a longer time scale. We can slow it down and watch the molecule move more slowly. You're seeing reasonable bond vibrations there. You see that the hydrogen and the carbons are wiggling relative to each other. But what we want to talk about now is rotation around the bond between these two carbons, okay? And one of the fun things is that in this app, you really get to see how temperature really is just kinetic energy. You see how as I increase the temperature, the molecule starts wiggling more? That's really all temperature is at the molecular level. It's kinetic energy. All right, so we'll turn the temperature back down, slow things down. This molecule is ethane, CH3, and it has one central carbon-carbon bond. Turn down the temp even more. And there it is. And you can see that there's a preferred orientation of those two carbons with respect to each other. Do you see how the atoms in front, let's see, the white atoms are hydrogens, the black atoms are carbons. I think you pretty much already got that, but let's be specific. Do you notice how the CH bonds on the carbon in the front are sort of interdigitated with the CH bonds on the carbon on the back? They're sort of staggered, that's what we call it. There's a reason for that, and it's because this staggered conformation is lower in energy than the alternative, which might be where the CHs are all lined up. The view I'm giving you of this molecule is called a Newman projection. It sort of collapses into two dimensions, the three-dimensional shape of the molecule. You look down the bond between the two carbons, and then you observe. And from this perspective, it looks like the CH bonds in the front are separated from the CH bonds in the back by an angle of about 60 degrees, right? And do you see how from this perspective, the carbons in the front, the CHs in the front, look like they're separated from each other from 120 degrees? Now you know that a bond angle on an sp3 hybridized carbon is really 109, but if you collapse it into two dimensions, it looks like 120. So that's called the Newman projection. Now I need to demonstrate to you that the conformation we've got here, and conformation is a term we use to describe a shape of an organic molecule that you get from rotating around carbon-carbon bonds. I want to demonstrate to you that this particular conformation, which we'll call the staggered conformation, is the low energy one. And to do that, I'm going to take one of the hydrogens and I'm going to propel her around. And actually we need to speed up the simulation so that we can do that easily. So let's see, propeller, no? Yeah, okay, there we go. Notice do you guys ever watch that old game show, The Wheel of Fortune? You know the wheel, is it tick, 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 and it's got the little thing that goes in between the pegs and then eventually it slows down. Watch this go through a similar thing. If I give it enough energy, why is that not working? Maybe we need a higher bath temperature. If I give it enough energy, you can see rotation around the carbon-carbon bond, but you can see that it always settles back. It always settles back into a staggered conformation. Did you see that? Did you see it go through a conformation where the CHs in front were lined up with the CHs in back, and then it went, right? The reason for that is, in purple, you're basically seeing the distribution of electron density around this molecule. And it turns out that if you line up the CHs in the front and the CHs in the back, there's electron-electron repulsion. And that electron-electron repulsion is worth about 3 kilocalories per mole overall for the molecule, or about 1 kilocalorie per mole per overlapped CH. So again, you can see that if we can rotate around that carbon-carbon bond easily, but that eventually it's going to slow down and settle back into a staggered conformation. So, take-home message number one, having groups on one carbon staggered with another is more favorable than having groups eclipsed with each other. Eclipsed is what we call it when they line up and overlap with each other in the Newman projection. Staggered is what we call it when they're interdigitated like this. All right? And again, that's because of electron-electron repulsion. There is another very important explanation called hyperconjugation. It's explained in your study guide. We won't talk about it a lot today, but I do want you to read it because it's going to come up again and be important. The idea is that in the staggered conformation, a CH bond in the front can overlap with a CH sigma star in the back to have a stabilizing favorable interaction. Okay, questions about what I mean by staggered versus eclipsed? Yes?
Is steric hindrance the same thing as saying electron-electron repulsion?
Yes. Is steric hindrance the same as electron-electron repulsion? The answer is yes. So you'll hear about this in the text. Steric hindrance, steric repulsion literally just means things with electrons bump into each other and can't occupy the same space. So, yes, and we would call that here steric hindrance. And that introduces something that your text may call torsional strain. Torsion means rotation around bonds. Torsional strain refers to the fact that some conformations about bonds are less stable than others because of steric repulsion, steric hindrance, electron-electron repulsion. Okay, yes?
In terms of torsional strain and steric repulsion, are they interchangeable terms more or less?
Steric repulsion is more general. Torsional strain is an example of steric repulsion. It's a special case. Yeah. Others? Yeah.
In the text it said that each, I think the difference in energy is 12 joules per mole.
Yeah, so in the text, your text likes SI units of kilojoules per mole. Organic chemists in general prefer kilocalories per mole because you got to have weird idiosyncratic sticklers about something. 4 kilojoules are about the same as 1 kcal, so when I said 3 kcals per mole, that is 12 kilojoules. Yep. You don't need to memorize that number. And the point is, the reason you want to know what the energy differences are between conformations is because then you can look at the temperature and predict whether you have enough energy at room temperature to overcome that energy barrier. If we were to draw an energy diagram about rotation around this carbon-carbon bond, we would see that energy, no, I did it again, somehow I can't get that to work. We would see that energy would increase as we go through eclipsed conformations and would decrease as we go through staggered conformations. The difference between staggered and eclipsed, as I said, is about 3 kilocalories per mole. At room temperature, you can actually do some math. You don't want to do this, but if you multiply like the gas constant times temperature, that'll give you about how much kinetic energy you have. Maybe it's 1/2 RT, about how much kinetic energy you have at room temperature. Anyway, 3 kilocalories per mole, room temperature, no problem. You can easily overcome that barrier. So, carbon-carbon sigma bonds are rotating constantly at room temperature. It's easy to go from staggered and eclipsed. All right? Let's just summarize this real briefly on note paper, because I know that it's hard to write down an animation. This is a side-by-side, this is a side view of ethane in a staggered conformation. Do you notice that this carbon-hydrogen bond and that carbon-hydrogen bond are anti to each other? That is, they're 180 degrees apart. If we take our view down the carbon-carbon bond between carbons 1 and 2, and anytime I do this, I just get distracted with evil Anakin Sith eyes. So So you can be, suddenly we're in episode 3 and you're shouting, I'm telling you, don't do it, Anakin, I've got the high ground. And then you say, I hate you. And, I don't know that that'll help you when you're taking a test, but that's right. You sit down at the testing center, you look at the test, and you say, this is the end of you, my master. I've actually had people write me like trash talk messages on the test, like they were psyching themselves up to take the test. Come on, Price, you got nothing. Yeah. Anyway, if we look down that bond, to draw the Newman projection, we'll use a circle, and the circle represents the bond sort of as a cylinder between the two carbons. In the front is carbon 1, and in the back is carbon 2. We'll draw, from our perspective, if we were looking down this bond, the hydrogen in the front that's highlighted in blue is going straight up. The hydrogen that was a wedge here is now coming to our right, and the hydrogen that was a dash is now pointing down towards our left. That's what we see for carbon 1 in the front. Carbon 2 in the back we can't totally see, but we can see the things that are bonded to it. Here is the hydrogen in the back that's anti to the hydrogen in the front, and then here are the other 2 hydrogens in the back. And that is the staggered conformation. A couple of just vocabulary terms, not that big of a deal. The relationship between the 2 blue hydrogens is anti, and then the relationship between the blue hydrogen in the front and the orange hydrogen in the back is gauche, which I think is a French word that means left, and that one is on the left, but there's another one on the right, and it is also gauche. Go figure. So 2 groups that are anti to each other in the Newman projection have a 180-degree angle between them. 2 groups that are gauche to each other in the Newman projection have a 60-degree angle between them. Okay? I'll draw real quickly the eclipsed conformation. In our side-to-side view, the eclipsed conformation would look like this. On carbon 1 on the left, all of the CH bonds are perfectly lined up with the CH bonds on carbon 2 on the right. You will see that the blue hydrogens are eclipsed with each other. If we put our sith eyes in the plane of the page and look down that bond again, what we'll see again in the front is basically the same thing, but in the back, we will draw everything lined up. Now, you can't do that perfectly, because if it was lined up perfectly, you couldn't see the CH bonds in the back. So you just need a little bit of an offset. But even this communicates that, yes, you're in an eclipsed conformation. And in an eclipsed conformation, the angle between 2 groups is 0. And what I tried to convince you of with that animation is the eclipsed is a high energy maximum, and then the staggered is a low energy minimum. And if we could label hydrogens, I'm just going to put a triangle on this hydrogen and a triangle on that hydrogen. You would see that there are 3 different eclipsed conformations and 3 different staggered conformations. So if this is energy, and this is angle between blue hydrogens, you would see that there is a staggered conformation where the angle between the, blue hydrogens or triangle hydrogens, either one. You would see that there's a staggered conformation where that angle is 180. There's a staggered conformation where the angle is 60, and there's, 120, and then there's a staggered conformation where the angle is 60. And then in between those, there are eclipsed conformations. And you could draw an energy diagram that would look like this, where rotation around the carbon-carbon bonds gives you this transition between eclipsed conformations and staggered conformations. And again, that transition is worth about 3 kilocalories per mole. Okay, in organic chemistry and in chemistry in general, maxima on an energy diagram are transition states. Molecules don't stay there for very long at all. Minima are places where molecules can equilibrate. If you have enough energy at room temperature to traverse these boundaries freely, then the molecule is going to be rotating quite easily. All right, questions about all of that? So let's now have you turn to your quiz. We want to do this same thing for the molecule butane. So here is the Lewis structure of butane. And I want you to focus on the bond between carbons 2 and 3 of butane. I want you to put yourself in the plane of the page and look down the bond between carbons 2 and 3. And I want you to draw, there should be 3 different staggered conformations that you can draw. And is that all I wanted you to do there? Yep. So your quiz says, I want you to draw a staggered conformation where the methyl groups are anti to each other, and a staggered conformation where the methyl groups are eclipsed to each other, and then compare them in stability. So go ahead and get started on that. I'd like you to take maybe 2 minutes to do that. If you can do it in 3, that would be okay too. Okay, you doing okay about there, or do you need a little bit more? A little bit more? Okay. Poquito. All right, let's gather back together. Let's see what you came up with. Just before putting anything on this Newman projection that we're going to draw, if it's a staggered conformation, remember you can draw the carbon in the front like this and the carbon in the back like this. Although if you want to be realistic, based on the way I drew the molecule, you can also draw the carbon in the front like this and the carbon in the back like this. Either option is okay, all right? It turns out this one works best with the way I drew it. If we put ourselves in the plane of the page, looking down this bond, the thing that's pointing downward would be the methyl group. Okay, so at confirmation where the methyl group in the front is anti to the methyl group in the back, should have, where should I put the methyl group in the back? Pointing up for that carbon in the back, good. All right. And then I need to remember, so the hydrogens. What is this hydrogen in the back gauche to? Methyl in the front and the hydrogen in the back, right? So each substituent on a carbon-carbon bond between sp2 carbons is going to be gauche to two things and anti to one thing. All right, let's draw the conformation. So this is the conformation where the methyl groups are anti. By the way, anti and gauche are relative terms. They specify the relationship between two groups. So it doesn't make any sense to call something gauche or anti unless it's obvious which two groups you're talking about. Here in butane, it is, because the two groups are that are most important on the front carbon, on the back carbon, are the methyl groups. So the gauche conformation, to do this, you can keep one of the two carbons 1 or 2, the same, and then imagine twisting the other carbon. And what you're going to do to convert one staggered conformation to another is imagine rotating each of those groups in the back 120 degrees so that they exchange positions. So then the methyl group in the carbon on the back is going to be here, and the two hydrogens are going to be there. You see that? Those are both staggered conformations, right? But here, the methyl groups are gauche to each other rather than anti. Okay, now the question was, which of these do you suppose is lower energy? Anti, yes, lower energy. Why? Yep, less steric repulsion, less torsional strain. You keep the biggest things on each carbon as far apart as possible, anti to each other, okay? To illustrate why this is, it's actually easiest to look at a space-filling model of butane. And so here it is. And we can, let's see, show it in space filling. Now we'll show it not space filling. Wait, that's mostly okay, let's do that. Looking down the bond between the carbons 2 and 3, we get the view that we expected, and that's the anti-conformation. Now it turns out we can look at the gauche conformation. And if you look at it from the side, it's not immediately apparent that those methyl groups are bumping into each other or that there's steric repulsion. But if we make that space filling, you can see that they definitely are. See how close those hydrogens are? So having methyl groups gauche to each other introduces electron-electron repulsion. Yeah?
So there's a question on the study guide where there's like a pentane. I think there's another methyl group.
Yeah.
And no matter what way you rotate it, it's always like the groups are always going to be gauche to one other methyl group. How do you determine which one is most stable when they all are kind of just the same? Is that different?
Yeah, so I'm not exactly remembering the problem in the study guide, but we could I think it's something like this. I mean, this is maybe the simplest example. that we could make more complicated. In fact, this might actually be on your problem set. And it looks like we're not going to get to drawing chairs today. That's okay, we'll do it next time. Let's look down the bond between 2 and 3. And just see what options we have. The thing that gets complicated here is on carbon 2, we now have 2 non-hydrogen groups, though on carbon 3, we only have 1 non-hydrogen group. So in this conformation, the biggest group in the back, which is the ethyl group, is anti to the methyl group in the front, but gauche to the alcohol in the front. And so the question you're going to ask is, which is better? In the spirit of Dwight Schrute, what kind of bear is best, or rather Jim's impression of Dwight Schrute? It's a ridiculous question. Yeah, which conformation is best? And to understand this, you've got to have a sense for how big a methyl group is versus an OH group. Let's just reason through that really quickly. How many things is the OH group bonded to? 2. So it's got 1 hydrogen coming off of it. How many groups is the methyl group bonded to? 4. It's got 3 hydrogens coming off of it. So it's probably a decent assumption that the methyl group takes up more space than the OH group. So you would want to keep the larger things anti to each other. This would be less stable because the 2 things that are biggest on both carbons are gauche to each other. Now I'll give you a quantitative measure for how big groups are so you can make these assessments. They're called A values. They're mentioned in the study guide. All right, that's enough for today. I will see you Friday when we'll talk about chairs. I'm going to adjust the study guide due dates accordingly, so don't panic.